Hey everyone, welcome back to the channel. In this video, I am going to explain the tests which are conducted on the transformer in order to obtain the equivalent circuit parameters and to find out the losses and hence the efficiency. How to find out the efficiency? That was explained in the previous video. If you haven't checked that video, you can check it from the link which is available in the description box. The equivalent circuits have been also explained in detail in the previous videos. The link for the same is also available in the description box. Now, when we had drawn the equivalent circuit of the transformer, the equivalent circuit has two different parameters. One is resistance and second one is reactance. And also the reactances are of the primary side, on the secondary side, and as well as reactance and resistance are there in the shunt branch of the transformer. So this is how the equivalent circuit of a transformer looks like, which is referred to primary side. R1 is primary side resistance, X1 is primary side reactance, RC is the core loss resistance, XM is the magnetizing reactance, X2 dash is the secondary side reactance referred to primary side, R2 dash is the secondary side resistance referred to primary side. In order to find out the value of these resistances and reactances, we need to conduct the test. Also, we have calculated the efficiency, which is given as V2I2 cos theta 2 upon V2I2 cos theta 2 plus Pi plus PCU, that is iron loss and copper loss. Now, how to find out iron loss and copper loss? That we can calculate from the two different tests. This will also help in calculating the voltage regulation that I will explain in the coming videos. Now, for finding out the equivalent circuit parameters and the losses, we need to conduct two different tests on the transformer. First one is open circuit test, which is also known as no load test. The second one is short circuit test. Now, from the name it is clear, open circuit means there is something which is going to remain open, and in short circuit there is something which is going to be short circuit. Now, what we can keep open and what we can short circuit in the transformer, that is only possible on the secondary side, because on primary side we always need to give the supply. So in case of open circuit test, the secondary winding is kept open, while in case of short circuit test, the secondary winding is going to be short circuited. So let's discuss them one by one in detail. So I'm starting with the open circuit or no load test. This open circuit test is actually performed on low voltage side at rated voltage and frequency. So when we are saying that it is performed at low voltage side, it means all the measuring equipment that is connected on the LV side, and HV side is kept open. High voltage side is kept open. So the Circuit diagram for performing the open circuit test looks like here we have transformer LV and HV. Since it's HV, so it's shown by more number of turns in comparison to the low voltage side, and this one is kept open as it is. We haven't connected anything to this side as we haven't connected any loads, so that's why the another name for this is no load test. We haven't connected any load to the transformer. On primary side we need to measure the voltage, so voltmeter is connected in shunt or across the two terminals of the primary winding. Ammeter is connected in series, and we need a wattmeter to measure the power whose current coil is connected in series and potential coil is connected in parallel. So this is how the circuit looks like. And the supply is fed to this single phase transformer through an auto transformer, or we can say variac, so that we can adjust the voltage. So here we will have single phase supply that will be adjusted through this auto transformer, or which is also known as variac, variable AC supply it means. So here we have the wattmeter which will give us the value of power at no load. The ammeter will give us the value of current at no load, and voltmeter will give us the reading of no load voltage or the rated voltage of the low voltage winding, since the test is conducted at rated voltage. So we will have the readings of three instruments, that is ammeter, voltmeter and wattmeter. Let's denote them by P naught, I naught and V naught. These are the three readings which we get from the open circuit test. Since the open circuit test is conducted at rated voltage, so the core losses, they are, which are directly proportional to the voltage, they are occurring to their actual value. They are not small, so whatever their actual value is there in case of transformer, they will be occurring in the open circuit test. Also on secondary side or the high voltage side is kept open, so the current which is flowing through the primary side of the transformer, that is only the no load current. Ammeter reading is actually giving us no load current, and this no load current is just 2 to 6% of rated current. Since this current is very small, so I square R losses, they are negligible when the secondary side is kept open. So what we can say, the wattmeter reading that actually reads the core losses, since I square R losses are negligible. So from the wattmeter reading P naught, which is wattmeter reading, we will actually get the core losses. What else we get from this? We have this wattmeter reading which is equal to V naught I naught cos of theta naught. So from here we can have the value of cos of theta naught as P naught upon V naught I naught, since we have the reading of voltage, current as well as the power. Once we have the value of cos of theta naught, we can calculate the core loss component of current, which is equal to I naught cos theta naught. We can also calculate the magnetizing component of current, which is equal to I naught sin theta naught. Now, if we look at the equivalent circuit, this is the equivalent circuit. The current which is flowing at the open circuit, if I just redraw this, equivalent circuit over here, on secondary side there is no load. We don't have any load on the secondary side. So this is how it looks like. So R2 and R2 dash and JX2 dash, they are not having any impact. The current which is flowing in the circuit is I naught over here. So this is equal to I1, since I2 dash is 0. Now since this current is very small, the drop across R1 JX1, it can be neglected. So when we neglect this, this equivalent will get modified to that this is the no load applied voltage, and we have a shunt branch over here, RC XM. The current over here is I naught, IC IM. Now voltage across RC is V naught, voltage across XM is V naught. If we know the value of IC and XM, then we can calculate the value of RC and XM. So RC can be calculated as V naught upon IC, and XM can be calculated as V naught upon IM. So this is how we get the value of two equivalent circuit parameters, that is RC and XM, from the no load test. Now we need to note down this, that this RC and XM, these are referred to LV side, since the test was conducted on low voltage side. So if we have to calculate them on high voltage side, or we have to calculate RC on high voltage side, then it will be equal to NHV upon LV square into RC LV. And similarly, XM on high voltage side, it can be calculated by NHV upon NLV square into XM LV. So if we have to draw the referred circuit on the high voltage side, so this thing we need to keep in mind over here. So we can summarize that from the open circuit test we can obtain the core losses and RC and XM. Now let's move on to the short circuit test. The short circuit test, it is performed on high voltage side. It is performed on high voltage side at rated current and rated frequency. So when we say high voltage side, it means all the measuring equipment that should be connected on the high voltage side, and the low voltage side is short circuited. and it should be short circuited through a thick wire. Since at short circuit the current is maximum, so we need to short circuit it by thick wire. Now how the circuit looks like: HV side, LV side. We can show them differently by showing high and low number of turns. So it should be short circuited through a thick wire. This is how the short circuit looks like. Then for measurement of voltage, we need to connect a voltmeter. Ammeter is connected to measure the current. Wattmeter for measurement of power, whose current coil is in series and potential coil is connected in parallel. Again, the supply to the transformer is given through a variac or an auto transformer, so that we can adjust the supply to see to adjust the rated current. So here we will have the single phase AC supply. Wattmeter reading PSC, current through this will be ISC, and that will be corresponding to the high voltage side. Now why we need to conduct this on high voltage side? Since the test is performed at rated current, the rated current for high voltage side is less in comparison to the low voltage side. Since the transformer operates at constant power, when voltage level is low, current level is high. When current level is high, current level is low, voltage level is high. So ISC, short circuit current on high voltage side, will be less in comparison to the short circuit current on the high voltage side. So we connect the measuring instruments on the side where the current is less, and same is the reason for conducting the open circuit test on the low voltage side. Low voltage side, lower voltage. Since we are going to perform it at rated voltage, we need the equipment corresponding to the lower voltage range, not according to the higher voltage range. In this case, we need the equipment or the ammeter corresponding to the rated current of the high voltage side. Low voltage side will have obviously much higher current in comparison to the high voltage side. Now when we conduct the test, the supply is varied until the rated current of the high voltage side starts flowing through the ammeter. Since the current flowing through the transformer is rated current, so the copper losses which are occurring in the transformer, they are full load copper losses. They will occur. Also, since this side is short circuited, the rated current starts flowing at much lesser voltage in comparison to the rated voltage. Let's say if the rated voltage of the transformer is 200, it's possible that the rated current will start flowing during the short circuit at 30 volts. Since the voltage is much less than the rated voltage, so the core losses which are proportional to voltage, they are negligible. So the wattmeter reading which we denote by PSC, that will actually give us the value of full load copper losses, that is the rated copper loss. So we have three different readings: power, current and voltage. PSC, ISC, VSC, wattmeter reading, ammeter reading, and voltmeter reading. Now, how the equivalent circuit looks like? If we compare to this circuit, this will be the change, that this side is now short circuited. This voltage, which is over here, V1, that is the applied voltage, it is VSC, which is much less than the rated voltage. When this one is much less than the rated voltage, so the no load current, that is also very small, and it is so small that we can actually neglect the shunt branch. So if we neglect the shunt branch, this is how the equivalent circuit looks like. So we have one resistance R1, second one is R2 dash, and this one is X2 dash. So this I need to modify if I haven't drawn it like this. So it should be X2 dash R2 dash over here, as well as, okay, here it's X2 dash and R2 dash only. This was a problem in copying. So this is how the circuit looks like. We have R1 and R2 dash in series. So RSC, the short circuit resistance, will be R1 plus R2 dash, which we can say actually equivalent resistance on high voltage side, since this test was performed on high voltage side. Also, XSC will be equal to X1 plus X2 dash, which is equal to X equivalent referred to high voltage side. Now, from the readings of three instruments, we can actually calculate this R equivalent and X equivalent. From PSC, which is actually giving us the I square R losses, we can write ISC square into RSC. So we will get the value of RSC as PSC upon ISC square. Also, from the voltage and current at short circuit, we can calculate the impedance. So once we have the value of impedance, then we can calculate the reactance also, which will be equal to ZSC square minus RSC square. So XSC is equal to X equivalent referred to high voltage side, RSC is the equivalent resistance referred to high voltage side. So this is how we can calculate them. Now if we have to calculate the equivalent resistance referred to low voltage side, then it will be equal to NLV upon NHV square into R equivalent on high voltage side X equivalent on low voltage side will be equal to NLV upon NHV square into X equivalent on high voltage side. Now depending upon on which side we have to draw the equivalent circuit, we can actually calculate the equivalent circuit parameters referred to low voltage side or high voltage side. And after this, we don't have any formula to separate the low voltage side and high voltage side reactance. So XHV is actually considered as XLV dash, which is equal to XSC upon 2. While the DC resistance can be measured and that can be cal from there we can calculate the AC resistance. So what we can summarize over here, that from the open circuit test we can calculate the shunt branch parameters, while from the short circuit test we can calculate the series branch parameters. Also we can calculate the core losses from open circuit test and copper losses from the short circuit test. In the next video, I will start solving the numerical problems based on transformers using the various formulas which we have developed in the previous videos, also using the different concepts of the transformer. If you feel that this video is helpful for you, do like and share this video. Also consider subscribing to the channel. Thanks for watching the video.